Okay, number 4, they want us to find the median or the mean here in the middle. So a couple different ways to do that. I know that it's going to fall because these are always perfectly symmetric, halfway between this 450 and 560. So I could add them up and divide by 2. Another thing I could do is what I care about is the distance from here to here, right? Could also tell me that. So if I also think how far apart are 560 and 450, so 560 minus 450 gives me what, 110? And so that means the distance from here to here is 110. So if I only want to know how far is it from here to here, let's say, just half of this, it'd be 55. Okay, why is that useful all by itself? Well, first off, that means 55 is the standard deviation, because this point of inflection is 1 standard deviation away, same thing as this one. And so the standard deviation is 55. And then I can also use that distance to find the mean. So it means if this distance is 55, if I'm at 560, this should be 55 less than that. And so the mean should be at 505 in the middle. Try to make some room to label it, so 505 centimeters. And we can check it from this side too. See if I go 55 above 450. So 450 plus 55 is 500, 505. And so either way, I get the median or mean here is 505 centimeters. Okay, then C and D are more interesting. They want the first and third quartile. Okay, so you can look at the formula for it, or if you want the description of the formula here, when you look at it and it says, I'll write the formula down here. Let's say for the third quartile, it's the mean plus 0.675 standard deviations. You'll see this number a lot because it's the third and first quartile distance. So even if you don't want to, you might accidentally memorize it. You don't have to memorize it for, like, let's say the test. I think I put this formula on there, but 0.675 is an important number that comes up over and over and over. So what is that number? Well, Q1 and Q3 aren't a whole standard deviation away. So if I think one standard deviation is 55, 55 represents taking a whole step over. I want to take 0.675 of a step. So more than half, but not quite a full step. So Q3 probably falls about there, and Q1 falls about there. And so what I care about is I'm not taking a whole standard deviation, I'm taking 0.675 of a standard deviation. So here, the standard deviation is 55, so what I care about is what's 0.675 times 55. Which gives me 37, just for this piece of it, 37.125. So I'm not, one standard deviation would be a step of 55. I'm taking a step of about 37. And I'm saying about 37 because they do say to round to the nearest centimeter, so they don't want decimal answers on here. Okay, so if the middle's 505, and to get to Q3, and so this is where the mean comes into the formula, the mean, or the middle, is 505. If one standard deviation is 55, I'm taking not quite a whole one, but this 0.675 of a standard deviation. So I want to be 37, about 37 above 505. So 505 plus 37 gives me 542. And you can also, this is why it's nice to have the pictures, you can also kind of eyeball, if this is 560, this should be less than that. So 542 seems reasonable, and this is the middle at 505. So I went about 37 above it. Not a full step, but a portion of a standard deviation. So Q3 is 542 centimeters. Okay, another reason that's useful is once you know how big 0.675 of a step is, the formula for Q1 uses the same thing. In fact, here, I'll just write it on top of this one. It's just that you go 1.675 of a standard deviation below the mean. So the exact same formula, just you subtract off 37.125 instead. So if I want Q1, the middle's at 505, and I want to know what's 505 minus this portion of a standard deviation that I'm taking off here. So that gives me 467.875. And we're trying to round to the nearest centimeter, so that's about 468, right? Because 0.8 rounds up. So Q1 is about 468 centimeters. And you can kind of look on the thing. If this is 450, it doesn't seem like a huge stretch that could be 468.